a persistent, low-frequency rumble that never reaches our detectors, hinting at a hidden chorus of ancient black holes. We are going to talk about a hiss. Not a sound you can hear with your ears. Sound does not travel through space, but a hiss in the data. A persistent, low-frequency hum in the geometry of spacetime itself. To find it, you have to look at a very specific number: 1 hertz. That is one complete cycle every 10 seconds. It is the frequency band that sits right in the gap between what ground-based detectors like LIGO can see, which is hundreds of hertz, and what space-based detectors like LISA see, which is millihertz, thousandths of a hertz. That gap has been nearly silent for decades, and that silence is exactly what makes it interesting. To understand why 1 hertz matters, you first have to understand what LIGO and LISA actually do. LIGO is a ground-based interferometer with arms 4 kilometers long. It detects gravitational waves from stellar mass black hole mergers, things like the famous GW 150,914, where two black holes of about 30 solar masses each collided. Those events produce a signal that sweeps upward in frequency, from tens to hundreds of hertz, in less than a second. That is the chirp everyone talks about. LISA, on the other hand, will be a space-based detector with arms 5 million kilometers long. It will see much lower frequencies, millihertz, from supermassive black hole binaries that take weeks or months to merge. Between these two, there is a gap. At 1 hertz, neither LIGO nor LISA is sensitive. That gap is where DECIGO is designed to go. DECIGO stands for Deci-hertz Interferometer Gravitational Wave Observatory. It is a proposed Japanese space mission. The name tells you its frequency band, deci-hertz, meaning tenths of a hertz. Its target is the range from 1 hertz to 10 hertz. That is the bridge between LISA and LIGO. DECIGO is not one simple detector. It is a constellation. The current design consists of 3 clusters of spacecraft placed in heliocentric orbit. Each cluster has 3 spacecraft forming an equilateral triangle with arms 1,000 kilometers long. Those arms are Fabry-Peyrotte cavities, optical resonators that bounce laser light back and forth to measure tiny changes in distance. The precision required is extreme. Relative mirror speeds must be controlled at the sub-micrometer per second level and alignment at the sub-micro-radian level. That is the machinery we need to hear at 1 hertz. But why is 1 hertz so special? One reason is that it is a clean window. Most astrophysical sources that produce gravitational waves at lower frequencies, like white dwarf binaries, simply cannot emit above 1 hertz. The frequency of a binary's gravitational wave is twice its orbital frequency. For a white dwarf binary to reach 1 hertz, its orbital period would have to be 20 seconds or less. At that separation, the two white dwarfs would be so close that they would merge. So above 1 hertz, the foreground from white dwarf binaries drops off sharply. That means the 1 to 10 hertz band is relatively quiet. There is less confusion from known sources. If you hear something there, it is more likely to be something exotic, something primordial. The exotic source we are interested in is primordial black holes. These are not black holes that formed from dying stars. They formed in the early universe, within the first fraction of a second after the Big Bang, when regions of overdense matter collapsed directly under their own gravity. They can have any mass, from asteroid-sized to supermassive. And if they exist in sufficient numbers, they could account for some or all of the dark matter. The key point is that primordial black holes are not expected to form in isolation. They form populations, and those populations produce binary systems. When two primordial black holes are close enough, they become gravitationally bound and slowly spiral inward, emitting gravitational waves all along the way. Now, here is the crucial connection. The gravitational waves from primordial black hole binaries are predicted to peak at frequencies around 1 Hz. This comes from the physics of their formation. Primordial black holes that formed during the QCD epoch, the quantum chromodynamics epoch, when quarks and gluons condensed into protons and neutrons, would have masses around 1 solar mass or less. Binary systems of such black holes produce gravitational waves that sweep through the Deci-hertz band during their in-spiral phase. That is exactly where DECIGO is sensitive. So the 1 Hz band is not just a gap, it is a target. It is the frequency where primordial black holes would announce themselves. To make this concrete, consider a specific theoretical prediction. In January 2025, a study published in Physical Review D, the paper by Afzal et al. On neutrino hybrid inflation, showed that primordial black holes formed in that scenario would produce a gravitational wave background with a peak frequency around 1 Hz and an amplitude of the energy density parameter of about 10 to the minus 9. That is a specific number, omega GWH squared times about 10 to the minus 9 at 1 Hz. That is within reach of DECIGO design sensitivity. The same study identified a parameter space where primordial black holes could make up the entire dark matter of the universe. So 1 Hz is not just a random frequency. It is a frequency where a specific, well-motivated physical model says the signal should be. But there is another, more immediate reason to take the 1 Hz band seriously. In November 2025, the LIGO Virgo Cagra collaboration reported a candidate event designated S250-1112 cm. This was a compact binary merger with a chirp mass in the range of 1 to 87 solar masses. That is below the mass of any known stellar mass black hole. The lighter component of the binary had a greater than 99% probability of being subsolar. The false alarm rate was estimated at about 1 per 4 years. The source distance was about 93 megaparsecs. If confirmed, this would be the first observational evidence for a black hole that did not form from a star. That is exactly the mass range predicted for primordial black holes from the QCD epoch. So the 1 Hz band is not just theoretical. It is connected to real data right now from the current generation of detectors. Let us connect the dots. The 1 Hz band is where the foreground from white dwarf binaries stops. It is where DECIGO is designed to operate. It is the predicted peak frequency for gravitational waves from primordial black hole binaries. And it is the high-frequency end of the in-spiral signals that could be seen by LISA as precursors to mergers that eventually become chirps in LIGO. So 1 Hz is not just a number. It is a meeting point. It is where the early universe, through primordial black holes, could be speaking to us in a steady, persistent hum. That hum would not be a single chirp. It would be a stochastic background, a hiss of overlapping signals from millions of binaries across cosmic history. Now, let us return to the silent torus idea from the previous episode. That was about the CMB quadrupole suppression and whether it might be a phase shift residue from a quantum bounce. That was about the very early universe before inflation. The 1 Hz hiss is different. It is about the universe after inflation, during the radiation-dominated and matter-dominated eras, when primordial black holes formed and began to merge. But there is a conceptual link. Both are about what is not said. The CMB quadrupole is suppressed. It is quieter than expected. The 1 Hz band is a window. It is quieter than the bands on either side. In both cases, the universe's silence is the clue. The absence of signal is itself a kind of data. We are looking for echoes, not from a topologically wrapped universe, but from a population of dark objects that have been merging in silence for billions of years. let us consider what DECIGO would actually see. The detector's sensitivity in the 0. 1 to 10 Hz band is designed to reach a strain sensitivity of about 10 to the -23 per root Hertz at 0. 1 Hz. That is incredibly precise. It means measuring changes in distance of less than 1/1000th of a meter over a 1,000-kilometer arm. At that sensitivity, DECIGO could detect the stochastic background from primordial black hole binaries with a signal-to-noise ratio of over 100 in a 10-year mission. It could also detect individual binaries that are too massive or too far away for LIGO and too rapidly evolving for LISA. So the hiss would be a composite, a loud, persistent background from the unresolved population, plus occasional loud chirps from individual mergers that stand out above the noise. There is also a connection to the event S250-1112 cm. If that event is indeed a primordial black hole merger, then its characteristics, mass, distance, sky location, can be used to constrain the primordial black hole mass function. The analysis of that event suggests that if confirmed, it would be consistent with the QCD epoch mass function that peaks in the subsolar range. That mass function, in turn, predicts a certain merger rate density. How many such mergers occur per year per cubic megaparsec? That merger rate density translates directly into the amplitude of the stochastic background at 0. 1 Hz. So the data from LIGO Virgo Cagra at high frequencies and the future data from DECIGO at low frequencies are linked. One informs the other. The chirp at hundreds of hertz tells you what to listen for at 0. 1 Hz. Now, let us address the practical challenge. DECIGO is not yet built. The current timeline targets a launch in the 2030s for a Pathfinder mission called DECIGO, which would have smaller arms and lower sensitivity. Full DECIGO would follow later. That means the 0. 1 Hz band is still, for now, silent. We have not heard the hiss yet, but we have designed the instrument to hear it. The technology is being developed. Optical cavities, drag-free control, laser stabilization, all at the required precision. The theoretical predictions are getting sharper, and the observational hints, like S250-1112 cm, are accumulating. So the question is not whether the universe might produce a signal at 0. 1 Hz. The question is when we will have the ears to hear it. Finally, let us bring it back to the personal moment. The scenario described in the introduction, a graduate student, late at night, sonifying LISA mock data and hearing a persistent hiss at 0. 1 Hz, that scenario is plausible. Sonification is a real technique used to search for patterns in data. A hiss at 0. 1 Hz would correspond to a signal that is continuous, not transient. It would not be a chirp. It would be a steady tone, repeated every 10 seconds, buried in the noise. And if that student then checked the theoretical predictions and found that the amplitude matched the expected signal from primordial black hole binaries, that would be a moment of recognition. Not a moment of fear, but a moment of awe, because it would mean that the universe has been whispering that signal for billions of years, and we have only just built the machine to hear it. That is the silence of the cosmos, not as an absence, but as a presence waiting to be heard. The 0. 1 Hz band is a window we have not yet opened, but the predictions are clear. Primordial black hole binaries would whisper there. The instruments are being built. The data is accumulating. The question is not whether we will listen. The question is what we will find when we do. And if that finding is a hiss, a steady, persistent hum from the early universe, then it will change the way we hear the cosmos, not as a series of dramatic events, but as a living, vibrating space, filled with dark objects whose silence is not absence, but the longest sound there is.